All right. In this lecture video, we're going to go over the reactions of ethers. So we went over how we can make ethers, and so now we're going to go over what ethers can do. So just like I said, ethers in general are fairly unreactive. But if I take ethers, because the oxygen of the ether is still partially negative. Remember, based on electronegativity, this oxygen is partially negative, so it still has some nucleophilic character. Now, in general, these are weak, not great nucleophiles or bases, but things like HBr and HCl, those are really acidic and very electrophilic. So if I take an ether and I react it with something like HX, HBr, HCl, what's going to happen is you're actually going to cleave the ether. So it's kind of like the reverse of the Williamson ether synthesis, right? In a Williamson ether synthesis, you take an alcohol, react with an alkyl halide to make an ether. You can go backwards if you use HX. So what happens here is the nucleophilic oxygen or basic oxygen, there's a proton transfer, so this attacks the hydrogen of HX to make the oxonium ion. Remember, this is a good leaving group now, or the oxygen is now a good leaving group. Because these are unhindered, X minus is now going to come in and break up one of these bonds to make the alcohol and the alkyl halide. Okay, and this can keep going, right? So if you have enough HX, you can keep reacting this to give you another molecule of the alkyl halide. Okay, so once you make this alcohol, right, if you use an excess of the HX, or if you're using this catalytically, if you have an excess of HX, this oxygen can be protonated do a proton transfer with HX, and then make this oxygen a good leaving group. Then X minus will attack this methyl group in an SN2 reaction to kick out the oxygen. Now, this works. This happens in a lot of different cases, but one of the things that you have to keep in mind is what are the alkyl groups that are attached to the oxygen here. Okay, so the acid cleavage to produce works well with HBr and HI. Okay, if the R group is tertiary, then the cleavage is a SN1 mechanism. If the R groups are aryl or vinyl, no substitution occurs there. Okay, you're not going to get any kind of attack on that carbon. So what does that mean? So what that means is, so for example, if I had this ether here, if I had tert-butyl methyl ether, and I reacted this with HBr, this is going to be an SN1 mechanism. So what's going to happen here, because this carbon is tertiary, I'm going to protonate. That's going to make the oxygen a good leaving group. And because this carbon's tertiary, it's going to be an SN1 mechanism. So the oxygen leaves spontaneously to make the tertiary carbocation plus methanol in this case. And then Br minus is going to attack that carbocation to give you the alkyl halide, where the halogen is on the most substituted carbon and the alcohol is formed from the less substituted carbon. This would be the opposite, right, if there was no tertiary group here. So if I had something like this, and I do the same reaction, HBr, what's going to happen is that you're going to do the same intermediate, but because neither of these are tertiary, the reaction is going to be SN2, and I'm going to put the alcohol on the more substituted carbon, and I'm going to make the alkyl halide on the less substituted carbon. Now, if the thing attached to the oxygen is a aryl group or a double bond, there's no substitution that takes place on that process. The other reaction of ethers that ethers can do is what is called autooxidation. So in the presence of oxygen, the ethers can auto-oxidize to this hydroperoxide species. And we need to, if you have ether, and so you probably have never looked at the cans of ether that we have, These have to be tested. You always have to constantly test ethers for the presence of these because these are very explosive. So this happens pretty slowly. Usually ethers, like the things like diethyl ether and THF, those are used pretty readily. So before this auto-oxidation happens, usually these ethers are used before this auto-oxidation happens. But you do have to check for this because this is an explosive species. Now the way this happens is through a free radical mechanism. So what happens here is that in the presence of oxygen, oxygen can initiate this process. And so what oxygen is going to do is that what is going to form some kind of initiator, and then it's going to abstract a hydrogen here to form a radical here. This radical is a relatively stable radical. You can think of radicals kind of like carbocations. So this oxygen is helping stabilize this radical, being a resonance effect, right? So I can draw a resonance structure here of that radical where this one electron goes here, one electron goes here, and I have one electron on my oxygen to give you an oxygen-centered radical that looks like this. Now this is a resonance structure, right? So just to show you that this radical is resonance stabilized, okay? Once you've made this radical species is now very reactive, and now it's going to propagate. So I know it's weird. Like usually when you think about drawing the Lewis dot structure of oxygen, you like to draw it like this. But when you take inorganic chemistry, what you learn is that based on molecular orbital theory, oxygen is actually paramagnetic. It has two unpaired electrons on there. And so oxygen's pretty reactive for that reason. So what's going to happen here is this unpaired electron is going to make a bond with one of the oxygens with one of the unpaired electrons on oxygen to give you a molecule that looks like this. Now we have an oxygen-centered radical here, right? And that oxygen-centered radical is going to react with another molecule of ether, abstracting the hydrogen in a radical process to give you the hydroperoxide and the radical, the ether radical. Now overall, the net reaction here, when you do this, is, so recall that the net reaction is the sum of the propagation steps, right? And so this process can terminate when two carbon radicals come in contact to each other. You get this molecule here. So the net reaction overall is that you're taking an RH bond and you're oxidizing it to the peroxide, the hydroperoxide. Okay, that's the overall reaction that's happening here. All right. So just to reiterate, ethers are pretty unreactive. The two reactions that you can do with them though are the cleavage of ethers and HX. The way the cleavage works is dependent upon how substituted the carbons are, right? If you have a tertiary carbon on the oxygen, it goes by an SN1 mechanism. If there's no tertiary oxygen if there's no tertiary carbon on the oxygen, it's an SN2 mechanism. Ethers can also undergo auto-oxidation via a radical mechanism to give you these hydroperoxide species. All right, thanks for listening. Let me know if you have any questions, and I will talk to you later.